Okay, in this lesson, we are going to continue our discussion on average velocity and instantaneous velocity so that we can look at how derivatives are derived. Okay, that's horrible. Just a reminder that your average velocity was your change in position over change in time. Okay, so that was this right here. That's how we got that. Then we looked at our instantaneous velocity. So that is, remember we first of all figured out average velocity and we realized that if an object moves at an average speed, we can't find what its exact speed is at any one given time in that interval. So if we want to find that speed at any one given time in that interval, then we needed to use limits to do that, and that gives us a way to find its speed at one given time. And that was that, and we'll talk about this again in a minute. Okay, our average rate of change is the slope of the secant line, and I'm going to show you what I mean by this in a minute. Okay. Yesterday we looked at average rate of change. So what we did is we kind of looked at, all right, if an object moved from here to all the way over here, let's say, okay, I looked at those two coordinates. I found the slope of the line and that gave me that average rate of change. Okay. Then if the problem was if I wanted to know, so that gave me how fast an object moved from position A to position B, let's say. But if I wanted to know exactly how fast an object was moving when they were right here on this spot, what I did is I looked at some intervals. So remember, I looked at points that were maybe that far apart, and then that far apart, and then that far apart, and I got them closer and closer and closer together, and I found the slope, found the slope, found the slope. Basically, I get them as close together as I can until pretty much the slope is basically this line right here, okay? This line right here is the tangent line because that line is on the outside edge of your circle, okay? That line, which is the slope, which is the tangent line, okay? When you find that slope, you are basically finding instantaneous velocity at the point where the line crosses the curve, okay? So I would be finding my instantaneous velocity at that point. When you are finding instantaneous velocity at that point, it is called a derivative, okay? You do it with limits. We looked a little bit about um, how to do that yesterday, okay? You do it with limits. You didn't know what you were doing at the time, but you were really finding a derivative, which is the biggest thing in calculus that you're going to use a ton, a ton, which is derivatives, okay? Um, Derivatives are noted by this little apostrophe up here, okay? Or sometimes derivatives are labeled as dy dx, that's what that's called, dy dx. It stands for change in y over change in x, okay? And again, that should be familiar too because this is really truly nothing more than a slope, okay? So hopefully that brings some things together here. Um, I want you to estimate the slopes at some certain points along this graph, the slope of tangent lines. So if I were to graph this tangent line right here, and it's really hard to tell because I don't have a scale, but if I were to graph that tangent line right there, you know, your slope is pretty close. I mean, obviously, it's a positive slope. I am going to estimate, I don't have a grid, so it's kind of hard, but I'm going to estimate that my slope is about 1. Okay? Here, if I draw my tangent line, it would look something like that. And it looks like it's a little steeper than -1, but clearly my slope is something like, maybe I go down 2 and right 1. I don't know. My slope is negative though, and it's probably steeper than a positive 1. Okay, here my tangent line would look something like this. And I will say that my slope is maybe, I don't know, 1/2. Okay. Steep right here too. Let's say your slope is -4. I don't know. Okay. And then down here at point E, your tangent line would look like this. And on a horizontal line, your slope is 0. Okay. I just want you to know that sometimes functions don't have a very well-defined slope at a certain point. And if that's the case, the derivative, and again, derivative, your notation for that is f prime of x or dy of x, but the derivative won't exist at that point either, okay? So I'm just going to tell you this. If you have dots or lines that come to a point, okay, there is no slope because it's not gradually moving as it comes into that point. And so there is no real definable slope because it's not gradually moving right here. Here, there is no slope at the point x equals 0, so the derivative won't exist at x equals 0 either. Here at x equals 0, it's kind of hard to tell, but your tangent line at that point would actually be a vertical line. Vertical lines have undefined slope, so your derivative at 0 won't exist on that graph either. And then here, if I look at x equals 0, the graph is just continuous at x equals 0. And as I move into this point, it's a different slope than as I move into it from this way. It's just continuous. The slopes are different from if I move into it from either angle. There is no slope. The derivative would not exist at that point. Okay. So what I'm going to do here is we are going to look at sort of the formal definition for a derivative, okay? This is going to seem long, and you will eventually learn the shortcut, but it is important that you know how to do this from the beginning, okay? So in the first case, I am wanting you to find the derivative of the function f at the point 4, okay? And I'm giving you the function as 2x squared minus 3. Basically, I'm asking you to find that if that function described a moving object, I'm asking you to find its instantaneous velocity at 4 seconds, let's say. Okay? Here's what I want you to do. I want you to say that a is 4. So I'm going to put 4 in right here. Okay? When I put 4 in, I have 2 times 4 squared minus 3, okay? Please make sure that you square the 4 first, then multiply it by 2, then minus 3, and you get 29. If I put 4 in for a here, then f of 4 plus h, okay, is going to be 2 times 4 plus h squared minus 3. This takes a little bit to simplify, but I do need to simplify it. Okay, so when I square 4 plus h, just remember that you can't square the 4 and you can't square the h. You have to multiply 4 plus h times 4 plus h. And I know you know how to do that, so I'm just going to tell you that you'll get 16 plus 8h plus h squared minus 3. So then, of course, this becomes 32 plus 16h plus 2h squared minus 3, which if we simplify all that becomes 2h squared plus 16h plus 29. Okay, now I am going to use my fancy dancy definitions of limits here. Okay, remember our a value was 4, so remember I put a 4 right here, and I put a 4 right here. Okay, so this is where I'm at right now. The limit as h approaches 0 of f of 4 plus h, which was 2h squared plus 16h plus 29, minus f of 4, which was 29, over h. Okay, so now you're going to simplify this a little bit. And I am going to have this. These 29s will cancel. Okay, and now I have 2h squared plus 16h over h. I can't plug h as 0 in right now. If I plug 0 in for h, I will have a 0 in the denominator, which I can't have. Okay, so I need to simplify this a little bit more algebraically so that it is legal for me to plug that 0 for an h value in. So I am just actually going to just factor out an h. I could factor out a 2h, but all I really need is the h's to cancel. So I will factor out that h, oops, and then I will have 2h plus 16 all over h. These cancel. Now, if I plug my h value of 0 in, okay, h is 0, I plug it in right there, And the limit as h approaches 0 is basically 2 times 0 plus 16, which becomes 16. Okay, if I was doing a velocity problem, my instantaneous velocity at exactly 4 seconds would be 16, whatever the units are. Okay, but I am, and the other thing is, I just found the slope of the tangent line. Okay, so if I graphed that function, 2x squared minus 3, and I looked at the x value of 4, the slope of my tangent line would be 16. Okay, and I actually have a picture of that here on the next slide. So the blue graph is the function 2x squared minus 3. Okay, I went to my x value of 4. So my x value of 4 is right here. Okay, my tangent line is the red line, and the slope of that red line is 16. That's what I just found. Okay, so here's the answer. I found the derivative at 4 to be 16, which means that the slope of the tangent line of the function 2x cubed minus 3, or 2x squared minus 3 it should have been, at x equals 4 is also 16. Should have been a square right here. Okay? Now what I want you to do is I want you to find an equation for this line right here, I already know that the slope is 16, okay? That's what I found when I did the derivative, is the slope of the tangent line is 16, okay? If I want to find an equation for that tangent line, what I would do is I would find a coordinate, okay? I know that my x value was 4, and when I plugged 4 into the function 2x squared minus 3, I got 29, remember? Okay, so I can easily do the y minus y1 equals m times x minus x1 and get an equation for that line. And when I do that, I will have my y minus 29 equals my slope of the tangent line, which is 16, and x minus 4. And I know you can simplify this. I'm not sure how this book will give you the answers to these, but it might be either way. But that's how you do that. All right, let's do one more. Now I want you to find the derivative at x equals 3 for the function f of x equals 1 of x, 1 over x. So basically, again, when you find the derivative, you're finding the slope of the tangent line at 1 over x. Okay, so here we go. I am going to have you realize that your a value is 3. Okay, so I'm going to find f of 3. F of 3 is 1 over 3, which is just 1/3. Remember, our function is 1 over x. Okay, f of 3 plus h is 1 over 3 plus h. Okay, this gets a little bit more complicated to simplify, so bear with me here. But what we're really doing, again, when we find the derivative, you're finding the limit as h approaches 0 of f of a plus h. I'm using this formula right here. F of a plus h is 1 over 3 plus h minus f of a, which is 1/3. I don't know why I have this f right here. Sorry, I'm going to get rid of that. Over h. All right. Now we can't plug h in right now. If we plugged a 0 in, we would have a 0 on the denominator, and that would be illegal. So unfortunately, we need to find a way to simplify this. Okay, what I am going to do is I am going to get common denominators on the top here. So I'm going to multiply this by 3 over 3. Then I'm going to multiply this by 3 over h over 3 plus h. Again, it's like multiplying by 1, but I'm getting common denominators. So now what I have is a limit as h approaches 0 of 3 over 3 times 3 plus h minus 3 plus h over 3 times 3 plus h all over h. Okay, if we simplify this a little bit here, we have the limit as h approaches 0. Okay, here's what I want you to think about. This negative right here needs to get distributed. Okay, when I distribute that, I have this 3 right here, and then minus 3 minus h over my common denominator, which is 3 and 3 plus h, and I still have that all over h. Okay, so a couple things happen. First of all, these two cancel each other out. 3 minus 3 makes 0. Then what I'm going to do is this. I am going to, instead of dividing by this h right here, I am going to multiply it by its reciprocal. Okay, instead of dividing by h, I'm going to multiply it by its reciprocal. So now what I have is I have the limit as h approaches 0 of negative h over 3 times 3 plus h times 1 over h. Okay? Hopefully you can see that these h's can cancel. And I'm now here. I have negative 1 over 3 times 3 plus h. Okay, now when I plug my h in, my 0 for my h, and I plug it in right there, it's illegal, or I mean it is legal, and I have negative 1 over 3 times 3, which is negative 1/9. Okay, so the slope of the tangent line of the function 1 over x at x was 3 would be negative 1/9. Okay. You can kind of think about this also, you guys. This is a formula that is the same basic formula, but it gives you a way to come up with, instead of finding something at a very specific point, you can come up with a formula that you can then plug any x value in to get that function, okay, to get the slope of the tangent line or the derivative. So we'll just do a couple of these too. Okay, same kind of formula right here. It's just that you're not plugging a number in this time. You're only plugging x values in. Okay, so here what I'm telling you is that f of x equals x squared. Okay, so f of x is x squared. I gave that to you. F of x plus h would be like plugging x plus h in. So that would be x plus h squared in this case. Okay, it would be x plus h squared, which becomes x squared plus 2xh plus h squared. If you don't know how I got that, I'm not going to take the time to do this, but I multiplied x plus h times x plus h because that's what squaring it means. Okay, so that's what I got. Again, what you're really doing is you're plugging in the point x, and I get x squared. I'm plugging in the point x plus h, and I'm getting x squared plus 2xh plus h squared. Okay, so you're still finding rate of change. Okay, you're still doing that. So this is like your x1, your y1, your x2, your y2, and you're finding rate of change with that. Okay, you're doing limits to do it in this case. But here we go. The limit as h approaches 0. Okay, because what you're wanting to do is you're wanting to add just a really small number to that x value so that you're finding super duper small increments between your values so that when your increments are small, it's closer and closer and closer to the tangent line. So that's what you're doing. It turns into from a secant line to a tangent line. Okay, if your h value gets closer and closer and closer to 0. So here's how this looks. Okay, f of x plus h we already discovered was x squared plus 2xh plus h squared minus f of x, which was x squared all over h. Okay, so what happens is these two guys cancel each other out. I can't plug a 0 in for h right now because I would have a 0 on the denominator, so I need to simplify. So what I can do now is I can take this quantity right here and I can factor an h out of it. If I factor an h out of it, I have 2x plus h all over h. Luckily, my h values cancel right now so that I don't have to deal with having an h in the denominator when my h is supposed to be 0. And I'm right here. Okay, now I can plug an h value of 0 in, no trouble. And I will have 2x plus 0, which just gives me 2x. What this does is it gives me a formula now to be able to find the instantaneous velocity or the derivative or the slope of the tangent line at any x value I choose. So now I know if x is 3, I can just do 2 times 3 and get 6. If x is 5, I can do 2 times 5 and get 10. Okay, at any x value I choose, I can now find the derivative, which is also the slope of the tangent line, which is also the instantaneous velocity at that point. Okay. And one more, again, this is very similar to what we already did, but this is a little bit tricky to simplify. So here we go. Our f of x is 1 over x, okay? And again, you're thinking about taking, by the way, 1 over x looks something like this. So you're thinking about taking 2 points that are first farther apart, and then you want to get them closer and closer and closer together until they're so close together that you basically have a tangent line, okay? That's what you want to do. When you do that, that's finding the derivative, which is the slope of the tangent line, which is the instantaneous velocity at that point. Okay, so here we go. That's why you want to add super duper small numbers to your x value until basically you're adding 0. Okay, so here we go. X plus h becomes 1 over x plus h. Again, I'm using this formula to find the derivative, and I want to reiterate that the derivative might be noted like that, or the derivative might be noted like that. If you see those two things in your directions in your book, it's asking you to find the derivative, and you can do that by doing this, okay? F of x plus h, we already know, is 1 over x plus h. F of x is 1 over x, all over h. Okay, again, can't plug 0 in for h right now because that would give me a 0 in the denominator. So I'm going to get common denominators. I'll multiply this by x over x, and I'll multiply this by x plus h over x plus h. And now, here I have x. And here I need to take this -1 and distribute it through the parentheses. So then I have negative x and negative h all over my common denominators down here, which are x times x plus h, all over my h that's still in the denominator. All right. These two cancel. So now I have negative h over x times x plus h. I'm going to take this h right here, and instead of dividing by h, I'm going to multiply by 1 over h. Okay. These h's cancel, and now I'm right here. Okay, and now if I plug my 0 in for my h value, I'm okay because x plus 0 is just x, so I have -1 over x squared. Okay, that is f prime of x, or it's dy dx, whichever you want to call it. That's what you get. Again, that allows me a formula to find the slope of the tangent line, or the derivative, or the instantaneous velocity at any x value I choose along my original function. Okay, and that should do it.